Good evening, and thanks for joining tonight's TI Technology webinar, hosted by Texas Instruments, where tonight we're going to take a magical mystery tour of fascinating sequences. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make those tough-to-teach, tough-to-learn concepts accessible to all my students. And with us tonight is Ron Lancaster. Ron's an associate professor emeritus at the Ontario Institute for Studies and Education of the University of Toronto, where he taught mathematics courses for pre-service, middle, and high school teachers for 17 years. Prior to that, Ron taught middle and high school math for 23 years in co-ed public schools and in an all-girls school. Ron's professional activities include consultations and conference presentations all across the world. He's been author for NCTM and the Ontario Association for Mathematics Education. Ron's also been a T-Cube national instructor for TI since 1994 and has conducted workshops throughout the United States and Canada on graphing calculators, motion detectors, and scientific probes. Ron's also the recipient of the 2015 Margaret Sinclair Memorial Award, recognizing innovation and excellence in mathematics education, awarded by the Fields Institute, and most recently, the 2022 recipient of the Lifetime Achievement Award from the Ontario Association for Mathematics Education. So, Ron, it's really great to have you with us tonight.
Thanks, Mike. It's great to be here as well. Thank you.
Ron, will you talk through some of the agenda items for tonight? What can we expect?
Yeah, so, there'll be a welcome like what you've done in introductions. We're going to take a tour of some really fascinating sequences. There's going to be 8 stops along the way. And we're going to look at the idea of developing some mathematical questions and rich tasks related to these sequences. So they're more than a curiosity. And we'll also be a number of times where I'm going to reference coding. So some opportunities for students to do some coding. That could be with the use of TI technology like the 84, the Nspire, or even Excel. And the three kind of sprinkled throughout this is going to be a lot of what if questions and tinkering with things. And then at the end, I have some suggestions for some resources. And at the end, Mike, you have a webinar drawing.
And I do. We're going to be giving away to, yeah, absolutely. We're going to be giving away to one lucky winner a TI graphing calculator of their choice. And Ron, just a couple other things for tonight. What can we expect to be able to do?
Well, I think one of the fundamental things, Mike, is the idea of for teachers, I can help students experience joy and moments of awe through these sequences. I can encourage students to ask what if questions. I mean, we're all trying to do that, but I'm hoping tonight that you get more examples of how you can do that with students. And also, I can help students use TI technology, to analyze these sequences, the idea of coding. And also becoming more aware of the resources that are out there connected to tonight's talk.
Thanks so much. We're expecting a large crowd, so your audio is automatically muted. Feel free at any time. Send questions to Ron using that Q&A window on the right side of your screen, and we'll also be using that chat window like so many of you are already using to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. And before Ron gets started, I just want to just full disclosure and appreciation for Ron being here. He had some really unfortunate events with weather at his house 24-ish hours ago, so very, very real. And so I know it's taken up a lot of his time recently and displaced him. And so I just wanted to say thanks so much, Ron, for sticking with it and being here. And I'm glad that you and your family are safe.
Thank you, Mike.
All right, Ron, you have control. Feel free to share your screen and let's get this started.
Okay, fantastic. Thanks, Mike. As Mike alluded to, on Saturday night at 6 p.m., I live in Hamilton, Ontario, and I'm in a beautiful street called Oak Knoll Drive, surrounded by massive oak trees that are well over 100 years old. And unfortunately, this is what happened. So an oak tree from my neighbor's property fell, and it just decimated my upstairs office. So just completely gone, where I do my work. And you can see the size of the tree. It came from our neighbor's property. That's my spouse's car. It's completely ridden off. It is just crushed. And neighbors' cars on the other side of the house also crushed. But this was just horrendous. In the last couple of days, it's just been crazy here, just dealing with stuff. I've had just surrounded by all kinds of activity. Thank goodness that, I'm getting a lot of help and that I have some insurance to help with this. But wow, I just really wasn't sure I was going to be able to prepare for this workshop. But anyway, Mike always inspires me to rise to the challenge and do it. So we've done it. As I mentioned in the introductions, we're going to take a look at some sequences. There are some standard ones that we use in the classroom, arithmetic sequences and geometric sequences and Fibonacci sequences. I think that these are really beautiful, and I think they're important to teach, and I also think they're fascinating. What's really interesting about the arithmetic sequences and the geometric sequences are that there's different representations for them. You can have recursive formulas, you can have direct formulas, and comparing all the different ways of writing these, and how would you come up with these equations? They're just fabulous, these sequences. I mean, they're simple, but they're fascinating. And there are some practical applications of all of these as well. Of course, the Fibonacci sequence is amazing. And that's defined recursively. And perhaps your students have asked you, is it possible to have a direct formula? So that if somebody asked you for the 100th Fibonacci term, the 100th term of the Fibonacci sequence, could you calculate it without knowing all of the 99 that come before it? And you may have seen this before. There's a thing called Binet's formula, and it's shocking. And it's a wonderful thing to show your students. You can actually derive this from a quadratic equation. You can look that up online. Just Google Binet's formula, and you'll find this. But who would have thought, that's connected to the Fibonacci sequence? How could this be? What's beautiful about this representation is you see that actually the Fibonacci sequence is sort of geometric, because for large values of n, the 1 minus root 5 over 2 is quite small, less than 1. Keep raising it to a power, and there's a limit. It tends to 0. And so you have something that's, approaching a geometric sequence. Just amazing. So anyway, I'm going to go beyond those sequences and show you some things that maybe you've seen before, and, but hopefully I'll have a few twists and ideas with these sequences for you. So let's go to stop number 1. This is the Borisov sequence. And my guess is that there is nobody who has ever heard of this sequence, the Borisov sequence. And you may be wondering, who is Borisov? So let's try this. Write down or think of a number. It's probably easier if you write it down or type it into something on your computer or on your mobile device. Just write down a number. It doesn't have to be as big as this. So just jot down a positive integer. I've used the first 50 decimal places of pi or something. I can't remember what I used here. But just, write down a 10-digit number or a 5-digit number or whatever. So have you got that? Okay. So what I'd like you to do is count the number of even digits in your number. Count the number of odd digits in your number. And then count the total number of digits. Well, you don't have to count that because it's the odd digits plus the even digits, the number of odds plus the number of evens. And tonight, Mike, if you can keep an eye on the chat as I pose some questions and things like that, that might make it a little bit easier for me so that I'm not kind of alternating back and forth between the chat with that. So for my number, I have 18 even numbers. I have 32 odd numbers. That may seem odd to you. I mean, shouldn't I have an odd number of odd numbers? It's a bad joke. But I have 32 odd numbers and I have 50 numbers. So what you're going to do is form a new number from that. So in my case, it's 18, 32, 50. So you write down the number of even digits 18 for me. The number of odd digits, 32 for me, and the total number of digits. So you have 18, 32, 50. So you're going to probably have something different than what I have. So you're going to see this a lot tonight where we do something over and over and over again. So let's count in your number the number of even numbers, the number of odd numbers, and the total number of numbers for your new number. So you have a sequence here. The first term is that gigantic number that I wrote down. The second term of my sequence is 183250. And the third term of my sequence is 336. So I'm forming a new number from the last number. And do it again. So in my case, I take 336. I have one even number, two odd numbers, and three numbers in all. So I've got 1, 2, 3. And if you keep going and going and going and going, it would be interesting to see if there's anybody tonight who doesn't get 1, 2, 3. Can you find a number that doesn't give you 1, 2, 3? And in the chat, if you found a number that doesn't give you 1, 2, 3, let me know. Mary Reeves just said that she got 1, 2, 3 as well. For this. And Jess Walker, yep, 1, 2, 3 as well. Mike, is there anybody posting anything saying that they did not get 1, 2, 3?
I'm looking, but I don't think I saw anyone.
Thanks, Mike. Because it turns out you're not going to get it. You're always going to get 1, 2, 3. Always. Which invites us to wonder, how would you prove this? And why is this happening? And by the way, you also might be wondering why it's called the Borisov sequence. Well, it turns out I'm actually teasing you. I am the only person in the world, probably, who calls it the Borisov sequence. Because one of my favorite songs from the 1960s was by Len Barry. So his actual name was Leonard Warren Borisov. And so he had a number of songs that he sang, but his most famous one was called 1, 2, 3. And it's a beautiful song. It's got a real nice rhythm to it. So that's why I call it the Borisov sequence. And it's actually interesting doing this because if you give it the actual name, your students can look it up. I mean, they still might be able to look things up here, but it's a little bit harder when you don't name it. The actual name of this sequence is the Sisyphus string or the Sisyphus sequence. It's got different names. You're going to have access to this PowerPoint file at the end, and you'll be able to read through this. And there's some resources there that you can look at. You can also read through this. This is a sketched out proof of why this works. It turns out if you use some coding, you can start to realize that if you pick a number above 999, it always goes down. Down, 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 down. And when you get below 999, it can fiddle around. It might go up, it might go down, boom, 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 boom. But if you want to prove this, all you need to do is check every number from 1 to 999. And you can use coding for that. Check all those numbers, all 999 numbers, and it turns out for those numbers, they all go to 1, 2, 3. What's a little bit tricky is proving that any number above 999, in fact, goes down. So that's, a little bit of a tricky part, to the proof. Anyway, I won't belabor this one. You can read this over afterwards and take a look at the resources, and it's really fascinating. So there's a lot of, what if questions your students can ask here. They can search for patterns. Can you predict how long it takes to get to 1, 2, 3? So if you collect some data, can you examine how long it took you to get to 1, 2, 3 in terms of the number you started with? Is there some connection there, to it? So there's lots of data students can collect and what if questions. What if you put the odds first and the even second, or the total number of numbers first. So there's different things like that you can do. So the second one. So take a look at this for a moment. I have a row of 4 numbers, and the 11, 5, 42, 33, those are numbers that I just picked arbitrarily. So I just picked them at random, 4 positive integers. And from those 4 positive integers, I did something with those to get the second row. My question to you is, what did I do? So Mike, in the chat, if you can kind of keep an eye on things to see, like, what do people think I did? How did I get the 6? How did I get the 37? Where's the 9 from? Where's the 22 from? What's my rule that I used? And there may be several variations of rules here. Jess Walker says the difference between them. Well, that's wonderful, Jess. I think if we were in a class and we had students as good teachers, we would say, tell me more. You said the difference between them. Like, what do you mean? Who's them? Like, tell me more. That's not good enough. So we would do that. We do it politely with our students, but we try and draw things out, so that they tell us more about what they're thinking with that. And Mary just had, and Mary, oh my goodness, Myra says it's a circle. And Emily Mazur says, I like the name Mary. And Michael Locker, the absolute value of the difference between blah, 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 blah. Whoa. So now we're really starting to get ultra specific here, in class. So there may be other possible rules here that your students have come up with, and your students could explore what happens with their rule. But let me show you the rule that I have in mind. The rule that I used is precisely the one that you've been coming up with. So to get the 6, I looked up and to the right. I had the 11 and the 5, and I took the largest number minus the smallest number. Now, a couple of you said, no. I took the absolute value, of the difference between the number above and to the right. And I think it was Mary who talked about the circle. To get the 22, you take the 33 and you go to the right. And so in fact, you have to go around the world. So go around all the way around the world and come to the 11, and you go 33 minus 11 and you get 22. If you're teaching elementary, this is actually a very simple sequence to use with your students. I mean, come on, it's just subtraction. This doesn't involve PhD level mathematics. You're just subtracting numbers. So it's a really wonderful exercise in basic skills, of having students to work with these numbers. So, as I mentioned earlier, what happens if we keep doing this? If we do it again and again and again? Well, in this case, with my 4 numbers, I ended up with a row of zeros. And when you get a row of zeros, you always get a row of zeros after that. So you might think that this is much ado about nothing, to quote Shakespeare. Well, it's a bad joke. It's not really much ado about nothing. But that's just for my case. So for your students, it's, do you always get a row of zeros? And this is where you can write a program for the TI-Nspire, and then you could enter in 4 numbers and you could watch what happens. In the Dropbox folder, you will have some programs that I've written, and I'll just show you one of them here. So, something I haven't, I won't do it here. Sorry. Forgot to load them up. But anyway, I have a program. I'll put it in the Dropbox folder. You'll need to transfer it to your handheld device. And when you run the program, it'll ask you for the 4 numbers. And then it'll just methodically, you just keep pressing the enter key. And it'll keep going. And it keeps track of how long it took to get the row of 4 zeros. You can also do this with an Excel file. So you could take an Excel file here and do this as well. So so you could take Excel, and there's a little bit of coding here with the absolute value of the difference between these, and then your students could play. So right now my numbers, in fact, I'll make this a little bit bigger here so that you can see this a bit better here. So, forget it. So anyway, my numbers are 12, 55, 45, 18. So you can go in and change the 12 to 12, 123005. And you're going to find if you use the program of the TI-84 or TI-Nspire or Excel, you're going to always get a row of 4 zeros. And it happens fast. It's like blistering fast to get your row of zeros. It's really tough to find an example that takes a long time to get a row of zeros. So there's a lot of tinkering here that you can do, that your students can do. They can try different numbers at the beginning, see if you always do get a row of 4 zeros. How long does it take? Is there a formula for how long it takes? So there's things like that that your students can do. So lots of questions for your students. Do you in fact always get a row of zeros? And how would you know? How would you prove that? And if you do always get a row of zeros, as I mentioned, what's the relationship between the number of steps and what you picked at the thing at the beginning? And what happens if you start with 5 numbers, or 6 or 7 or 8 or 9 or 10 or 50? Well, again, with coding, it makes it possible. With the Excel spreadsheet, you can easily set that up. You can modify the 84 program, easy. When you know a little bit of programming. And if programming scares the heck out of you, then just, find a kid in the school who's interested in programming and, let them take over and let them help, to develop some coding, for you. If you're at the elementary level, what's probably the easiest to do is to use Excel. And if you haven't got a clue how to use Excel, just tell your class. Some of your parents, there's got to be somebody in the room whose parent uses Excel in their workplace. Would you mind if I talked to your parent so that they could help me with Excel? And anybody who uses Excel will be able to, set this up. It's fairly basic. I used that a number of years ago. I was teaching in an all-girls school and I didn't know much about Excel. And so I asked the girls, I said, there must be one of your mums who uses Excel. And I had a whole bunch of mums calling me and I met with them and I learned a lot about Excel, from them. And, for the students, it was nice for them to see me learning from somebody else, as well. So anyway, why don't you try one of these right now? So just pick one. Just pick one of these. So if you want to pick the first one, 1, 2, 4, 8, that's your 4 starting numbers. Use the rule, keep going, and how many steps does it take to get a row of 4 zeros with that example? Some of you might want to take the one in the lower right corner, the 1, 7, 49, 33, 43, and do that one. If I were in a classroom right now with you, I would assign all of these around the room. So, one group over here would get the first one, another group would get the second one, the third one, fourth one, fifth one. But I think for our purposes here, just pick one and just see how long it takes. And in the chat, if you could just put in the example you picked, 13927, and how long it took. So how many steps did it take to get a row of zeros? All of these, in fact, do go to a row of zeros because it turns out everything goes to a row of zeros. So, Mike, if you could keep an eye in the chat and just see what kind of data we get here. You're going to notice that these are all geometric sequences. So if you're teaching geometric sequences or exponents, this is a place where you could use this activity. So you could go over this 4 numbers game with your students. Here's the rule, and take these cases and see how long it takes. And what do you notice? And even with elementary students, they could do this as well. They could take 4 terms of the Fibonacci sequence. They could take 4 terms of an arithmetic sequence. They could do a bunch of things here for the 4 terms and see what happens. So instead of just doing 4 random numbers, pick 4 numbers that are kind of connected to each other. So Mary Reeves, I just missed that. Mike, what are you seeing here?
So I think for Mary, I saw 1, 6, 36, 216, and got zeros in the 7th row.
Oh, okay.
And then Gray did 1, 2, 4, 8, and it took 7 steps.
Same with Jess. I just saw Jess.
Yep,
By the
7
way, the
steps.
number of steps it takes doesn't include the starting numbers because you haven't done anything yet. Anything else, Mike?
Not right now.
Okay. So, that's the idea with this investigation. Have your students collect some data. Here's what they're going to find out. Every single geometric sequence, and if you don't want to use that word, everything like this pattern, if you do 1, 8, 64, 256, if you do 1, 10, 100, 1,000, every example takes 6 steps. I know we were getting some 7s there, but it's probably because you were counting the initial step, the initial set of numbers as a step. So the way I'm doing this here is I'm not including that. So that's probably why folks were getting a bunch of 7s. It turns out the first example takes 7 steps. And it's like, what's going on here? Like, why is it that the first one takes 7 steps, but everything else takes 6? What's going on here? At the elementary level, your students are going to have a hard time, proving anything about this, but it's going to be a mystery to them. Like, gosh, I mean, why is this happening? Why is the first one the only one in the world that takes 6, 7 steps? And what I mean by the only one in the world is this pattern, 1x, x squared, x cubed. If you're teaching at the high school level, you can actually look at this algebraically. So you can take 1x, x squared, and x cubed, and then you can do it. Problem is that you have to decide which is the largest and which is the smallest. The absolute value isn't going to cut it here because it's going to become this monstrous mess. So you have to think it through. And if you just think about it in terms of graphs, if you graph y equals x squared and y equals x cubed, you'll see that if x is greater or equal to 2, that x cubed is bigger than x squared. So you don't go x squared minus x cubed, you go x cubed minus x squared, and so on. And, if you take this and just keep going, you will, you'll understand why x equals 2 is an anomaly. It's the weird one. There's something that happens. You can look this sequence up, and I'll be putting some journal articles in the Dropbox folder that will give you more information. Now, if you're at the elementary level, this might not be the best example to use, because you might be uncomfortable with the fact that there's no closure. So maybe what you could do is give your students this. Say, if you use these fractions and play the 4 numbers game, how long does it take to get a row of zeros? And this is like brutal. Oh my goodness. It's what this invites your students to do is to ask, is there a better way of doing this? And if you multiply every one of these fractions by the least common denominator, you'll be able to wipe out the denominators. As it turns out, you don't change the number of steps to get to a row of zeros when you multiply. So for example, way back at the beginning, my first example, those first 4 numbers, I could make them 22, 10, 84, and 66. It's going to take the same amount of time. You can multiply the numbers by anything you want, and it does not affect how long it takes. So what you need to do with that fraction one is just multiply, everything so that you get rid of the denominators. Maybe you could start by multiplying them all by 55, multiply them all by 12, multiply them all by 30, multiply them all by 15. That's way too big, but it works. And then you just have some positive integers, to work with. So the fractions might be an interesting thing at certain levels of elementary, where you teach fractions. You could allow integers as well. So you could do this with integers. Instead of 4 positive numbers, 4 positive integers, you could do 4 negative integers as well. So it turns out in this case that what I meant to say was the least common multiple, and it's 660. So if you multiply them all by 660, now you just get some positive integers to do. So it's interesting. It's a way for students to try to wrestle with, how am I going to do this? What is a better way to do that? If you teach at the high school level, what happens if you use irrational numbers? Oh my goodness, this is a nightmare. Because if you're going to use any technology, you got a problem. Unless it's Inspire, that can work with exact representations. So I'll leave that for you to think about. There's also complex numbers that you could use. And this is a problem because which is the biggest and which is the smallest and so on. By the way, that complex hotel there, I used to run a contest where people had to figure out where I took this picture. And that contest, one of the places it ran in was this newsletter a number of years ago. By the way, this newsletter is put out by Chris Smith in Scotland. He is a passionate teacher. And he puts out this newsletter almost every week of the year. And it's always got something in there that's really cool that you can use with your students. So what I would suggest you do is email Chris right now or at the end of the webinar. Email him, don't forget, and just tell Chris you want to be on his mailing list. Chris is not going to sell your email address to somebody. He's not doing this for money. It's just a labor of love. And he's been doing it for years. So, but it's really nice, So there's Chris's email address, and you can contact him. He's in Scotland, and so you can send that off to him. So this will be in the Dropbox folder, his email address. By the way, just a comment here. I mentioned earlier that it's really hard to find an example that takes a long time. So at the elementary level, you could just have a contest with your students. Who could find an example of 4 starting numbers that takes the longest? That's a great activity for young kids. And so they do the calculations and they work it out. But wow, your students are going to really have a hard time finding an example that takes 7 steps or 8 steps. Look at the example I tried here. Look at my 4 starting numbers. Gigantic numbers, small numbers. 4 steps to get a row of zeros. Unbelievable how fast it happens. It turns out that it's possible to find a set of 4 numbers that takes a long time. And this is for the high school folks here. I'm just going to show you a set of 4 numbers that takes 37 steps. And this is just shocking. So, if you're standing up, sit down. Because this is just unbelievable. That's the set of 4 numbers. And it takes 37 steps. What's shocking is where those numbers came from. You ready? You sure you're sitting down? Here it is. Oh my goodness. Those 4 numbers are coming from cubic equations, the roots of the cubic equations, and on and on and on and on. It's just, oh my goodness. Like, what in the world is going on here? This is just beyond belief. So it's like, good grief. So this is only for some of your students. There's enough here for elementary students to use and high school students, but this is a bonus. Anyway, this will all be in the Dropbox folder. You can come back and take a look at it, and I'll have a journal article in there for you as well. So stop number 3. So this is a really cool one. I have a very good friend of mine that lives in 153 West 76th in Manhattan. And the first time I met her decades ago, she told me her address. And I said, 153 is my favorite number. And the reason is if you go 1 cubed plus 5 cubed plus 3 cubed, you will get 153. Which is like, wow. So can you find some other numbers that are like this? So pick a number a 3-digit number, a 4-digit number, a 5-digit number, whatever you want to pick, and cube the digits and add them up and see what you get. And when you do this, what do you notice? Like if it doesn't work like this, is the number you get bigger than what you started with? Is it smaller? You know, what do you see? And what if you did this with squaring the digits or raising them to the 4th power? So this is just basic multiplication with this. It turns out there are 4 numbers that have this property, and they happen to be 3-digit numbers except for 1. So if you take 371, 3 cubed plus 7 cubed plus 1 cubed, it's 371. They have the same property. Crazy, these numbers. So again, it's, can your students find those numbers at the bottom? And perhaps coding is a way of doing this with that. So you can read this over afterwards, but the really interesting thing at the elementary level or the high school level, if your students can multiply and if they can add, pick a number. Just pick 59. So go 5 cubed plus 9 cubed. You get 854. Do it again. Do it again. Do it again. Do it again. What do you notice? What do you see when you do this? When you keep going? Don't worry about the bottom part. I mean, that's kind of a high school thing. But the beginning of this is just cubing the digits. Just doing a multiplication and adding them together. So that'll be a great activity for your students to take a lot of different starting numbers, cube the digits, keep going, and see what happens. And it turns out there's some really crazy things here. If you start with 59, you'll eventually get 371. And that's one of those special numbers. 3 cubed plus 7 cubed plus 1 cubed is 371. And here's all the things that will happen. If you start with 1, you're always getting 1. If you start with 999, you'll eventually get 153. If you start with 2971, you'll eventually get 370. And if you start with 98, you'll eventually get 407. And if you start with 55, you get 250 and then 133 and then back to 55. It's looping around. So these are the cases that your students will come up with. So, and again, coding might help here to use Excel, to collect some data or a program for the TI-Nspire. But these are all the different cases that you can get. So no matter what number you start with, you are always going to get one of these cases. If you start with 919, you're going to get 1459, then 919. And there's other numbers that lead to 919. So there's a whole bunch of numbers that will go to 919. There's all kinds of numbers that will go to that 55. So you're going to get all these numbers together. And imagine on your bulletin board, if you take, all the numbers that go to 153, put stickies up. These are the numbers that go to 153. These are the numbers that went to 370. These are the numbers that went to 371, to 407, to 55, to 136, to 160, to 919. So, taking all the numbers and putting them together that way, and what do they have in common? Can you predict, where they go with the starting number? So it's just all about looking at the data and, just seeing all of this. Again, those are some screenshots from a graphing calculator program that does this. It turns out that it is possible to predict it. If you're teaching at the elementary level, don't be scared by what you're reading here. This just says that if you start with a number that is a multiple of 3, I guarantee you're going to end up with 153. If you start with a number that when you divide it by 3 and get a remainder of 1, I guarantee you're going to get one of those cases. You're either going to get a 1, a 55, a 136, a 160, 370, or 919. And if you take a number and divide it by 3 and you get a remainder of 2, you're going to get a 371 or a 407, guaranteed. So it's all about looking at the numbers and dividing them by 3 and looking at the remainders. And like at the high school level, it's like, why is this working? In the second case, how can you predict which one of those it goes to? So if you have a number that when you divide it by 3 and get a remainder of 1, there's a whole bunch of possibilities. How can you refine that further, as well? Mike, are there any comments in the chat about this one?
Michael just had a good comment. If you use higher mods, can you separate case 2?
Yes.
And I'm not even sure that everyone on tonight might know what a mod is. That was something new to me a couple years ago.
Yeah. A mod is just what we're doing here. Like when we say that, let's take 62. If we divide 62 by 3, it goes in 20 with a remainder of 2. So what you say is that 62 is equivalent to 2 mod 3. It's the remainder that you get when you divide it by 3. So that's what modular arithmetic means. But yeah, so there is a way of actually, categorizing those even more. So that would be great at the high school level. But at the elementary level, it's just a really cool thing to get all of those cases, and to see, like, what do they have in common? Your students will definitely notice the multiples of 3. Every one of the ones that went to 153, they are all multiples of 3. You'll see that. And that's a bit of a clue that maybe we should look at the other cases and think about, how they're connected to, dividing by 3. So these are called narcissistic numbers. So the numbers are in love with themselves. 1 cubed plus 5 cubed plus 3 cubed, it comes back. You get 153. It loves itself. It likes to display itself, as well. So our fourth example. This one is, one, I have some others in a moment that are perfect for, elementary. But this one here, I know this looks complicated. All this says is pick 2 numbers. Pick 2 positive integers. And you're going to get a third term of the sequence. So the first term is 8. The second term is 2. And what do? You take the last term and you add 1, and you divide it by the term before. Here's an example. So I started with 8 and 3. So I got the 0.5, the third term, by taking the 3 and adding 1. That gave me 4. And I divided it by 8. And I got 0.5. Do it again. Take the 0.5 and add 1, 1.5, and divide it by 3. And I got 0.5. And then add 1, divide it by 0.5, and you just keep using this rule. It turns out you get into a cycle. No matter what 2 numbers you start with, you will always get this cycle of numbers. You're going to cycle around. You won't get this cycle of numbers, but your first 2 numbers are going to come up again after 6 steps. So it has a period of 6. This is really nice. I mean, actually for elementary, this is pretty good because it really just involves fractions. You're eventually going to be dividing fractions. I've written this as decimals here, but it might be preferable to write the 0.5 as a half, because you're going to get into things where you've got, big repeating decimals like 0.123, 123, blah, blah, blah. So it's better to do it with fractions. But it's a really nice basic skill question. But, can you find an example that doesn't cycle around after 6 steps, when you're doing this? And what do you notice? Can you find an example that takes more than 6 steps to cycle around? And at the high school level, you could prove this, and show that, it actually always works. So this one is actually an interesting one because there's my 2 numbers. I started with 7 and 6. And you can see that I took the 6 and I added 1. I got 7. 7 divided by 7 is 1. That's why the third term is a 1. Take the third term, the 1, add 1, get 2, divided by the term before, which is 6. 2 divided by 6 is a third. Take the third and add 1, 4 thirds, divided by the term before it, 4 thirds, and so on. And this also loops around, comes back around. What's really cool here is if you take that sequence and form some points. So do you see how I've got these points? Took the sequence and I went 7, 6, that's the first point, 6, 1, second point, 1, third point, and etc. And I got those points. And if you graph this, you'll actually get an image like this. And it's lots of interesting questions. What's the area of this? Are there any right angles? And just on and on and on. What happens if you pick 2 other numbers at the beginning? What kind of picture do you get when you do it? And for those of you at the high school level, instead of adding 1, you could also add 0.9. And so there's all kinds of questions here. So this is where you add 1.1 instead of adding 1. Believe it or not, that's what you get. This is just insane stuff. So this is at the high school level, this one. Anyway, I don't want to turn you off with some of these, especially if you're at the elementary level, but I think there's elements of this that you can use with your students, and it invites them to want to learn more mathematics so they can understand this. As a math teacher, you may be worried that you're exposing students to something that they're not going to understand. But I guess my advice to you is get over it. Because really, when a young kid asks, why is the sky blue? Do we go into a PhD dissertation about why the sky is blue? Do they really understand why the sky is blue? Of course not. It's really complicated. So should we not tell students that the sky is blue? Never ever talk about it because they're going to ask? No. I mean, kids learn lots of things that they don't understand at the moment, but it invites students to want to learn more. They hear a song, a complicated song. Do they know how to play it instantly? Of course not. They need to learn more, to be able to do that. So I wouldn't be too worried about exposing students to, a few things here and there that are complicated. So I have 4 other examples for you to look at. And there'll be information in the Dropbox folder on these. The first one is the hailstone sequence. This is a really beautiful sequence. This is where, if you want to try this right now, just write down a number. So just write down a positive integer. Have you got your number? If you have an odd number, multiply it by 3 and add 1. If you have an even number, divide it by 2. So if you started with 7, you would multiply by 3 and add 1 and get 22. If you started with 84, you'd divide by 2 and get 47. Or, oh, geez, bad day. But so 42, you divide by 2 and get 42. Then do it again. So if you start with 7, multiply by 3 and add 1, get 22. You now have an even number, divide by 2, and you got 11. Now you've got an odd number, multiply by 3 and add 1, 34, and keep going. The hailstone sequence is a fascinating sequence. It's just basic mathematics. It's multiplying by 3 and it's adding 1. That's all it is. It turns out that the hailstone sequence is one of the most famous sequences in the world because what mathematicians have found is that every single number up into the billions goes to 1. Nobody knows why. Nobody has ever found a number that doesn't go to 1. And if you do a Google search, as we just suggested for the collapse conjecture, there's a ton of stuff on this. But you could explain this to a kid in grade 4. You're multiplying by 3, you're adding 1, you're dividing by 2. This is not PhD level mathematics. But there's all kinds of experimentation here. Try different starting numbers. See what happens. Watch the numbers, how they go up, how they go down. They go up, 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 how they go down, down, down. You know what happens. It turns out as soon as you reach a power of 2, it's over. If you get 32, divide by 2, 16, 8, 4, 2, 1. And as soon as you get a 1, you're in a little cycle. 1's an odd number, multiplied by 3 and add 1, get 4. 4 is an even number, divide by 2. 2 is an even number, divide by 2, get 1. You're back to 1. It's going to be 1, 4, 2, 1, 4, 2, 1, 4, 2. And there's so many questions you can ask here. You know, what number would lead to 53? You know, what would you start with to get 53 with the hailstone sequence rule? So much stuff with the hailstone sequence. It's really amazing. The look and say sequence, I'll show you more of that in a moment. The Capricor's constant is a really beautiful one. You take a 4-digit number and you just arrange the digits from in decreasing order and increasing order, and you do a subtraction. You can Google Capricor's constant. It just involves subtraction. And it turns out, no matter what 4-digit number you start with, you will always get 6174. And it's interesting to see how long it takes. I won't go into the details here of what the algorithm is. You can look up Capricor's constant and you'll find a whole bunch of stuff, you know, on it. But it's beautiful. And the divisive number 15 is really cool as well. So so there'll be stuff in the Dropbox folder in the divisive 15. So you'll see that. I just, I wanted to put in a bunch of extra things here as well, so that you have 8 things to play with. And my goodness, I hope that there's at least one thing here you can use, of all of these 8. Depends on what grade level you teach, of course, but I hope there's at least one thing, that will be something that you can use with your students, depending on, as I say, what grade level you're teaching. But those are 8 different things. These 4 on this page here, you can easily look them up, and find information. As far as resources go, one of my favorite all-time books is this one here by David Wells. It's the Penguin Dictionary of Curious and Interesting Numbers. And most of the ones that I've looked at tonight with you are in this book. What's really cool is you can look up a number. So let me do it here. I'm going to look up the number 243. It gives me information about 243. I can look up 247, and it tells you something about the numbers. It's a beautiful book by David Wells. He also has the Curious Dictionary of Interesting Puzzles, the Curious Dictionary of Interesting Mathematics. His work is fantastic. So that's a great book. The Book of Numbers by John Conway. It's also filled with a lot of kind of quirky, unusual stuff. Just things that kids normally don't see in high school or in elementary school. Just really wonderful stuff. In Peter Fox, Mike, what did Peter Fox say about 153?
He said he's guessing that if you took number 153, it says that would be a narcissistic number.
Absolutely. You bet. So I'm looking up 153 in this book. Oh my goodness. 153 is also 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial plus 5 factorial. And it's got all kinds of other stuff. And finally, my all-time favorite book is by Richard Phillips. And you can probably get a used copy, Numbers, Facts, Figures, and Fiction. And this is the coolest book because when you open it up, it's just gorgeous. You can look up numbers here, and it has photographs, it has properties of the numbers, and a lot of these sequences that I mentioned tonight are in this book. So they appear here as well. So it's Numbers by Richard Phillips out of England. And there's, any book by Martin Gardner would be worth its weight in gold. So you'll find, more things like this as well. But those 3 books I mentioned there are probably, my favorites that I really like, and particularly the Martin Gardner books too. So that's some pictures that you'll have in the Dropbox folder. So you'll have some images of the books, so you can, look them up online, and find them. By the way, I mentioned the hailstone sequence. Oh my goodness, imagine on the wall of your school or in the wall of your classroom doing this. So pick a number right up here, and this is right here. There's where 29 is at. 29 is an odd number. Multiply by 3, add 1, get 88. 88 is an even number. Divide by 2, get 44. 44 is an even number. Divide by 2, get 22. 22 is an even number. Divide by 2, get 11. 11 is odd. 3 times 11 plus 1 gives you 34. And then you get 17, you get 52, you get 26, you get 13, you get 40, 20, 10, 5, 16, 8, 4, 2, 1, boom. So you're charting the path, that the numbers are going to. And it's just, oh my God, I mean, this is just unbelievable on the walls of your school, where you've got all these numbers coming into one. And then you can have a song playing in the background by Three Dog Night. 1 is a lonely number. It's not. That's a lie. Because everybody goes to 1. At least that's the conjecture. So I think you'll love doing this with the hailstone sequence. It's so visual. It's really cool. This is a great comic. The Collatz conjecture says that if you pick a number, blah, 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 and if you do it long enough, eventually your friends will stop seeing you. They won't want to hang out with you. Anyway, this is the look and say sequence. So you start with 1, and what do you see? You see 1, 1. So that's why the second term is 1, 1. Now what do you see? I see 2 1s. And with the 21, what do you see? I see 1, 2, and 1, 1. And with the 1211, I see 1, 1, 1, 2, and 2 1s. So you say what you see. And this thing just, goodness, the numbers go crazy in the size. This will be a beautiful thing in the wall of your classroom as well. So that's the look and say sequence that I mentioned. This is Capricor's constant. I forgot that I put some details in here for you about Capricor's. So you'll be able to look that up. And the divisive 15 as well. So I do have that. So if you want to get some files, I need to put them in tonight. I'm sorry that they're not there immediately. I just got Wi-Fi about an hour ago, 2 hours ago. And this whole day has been frenetic. I mean, I've been desperately trying to get Bell Canada here to hook up our phone lines, which are ruined, to get internet on. So I'm sorry, I haven't had time to put them into the Dropbox folder. So, hopefully you'll bear with me and give me a couple hours to put stuff in. And I promise you I will, put files into the Dropbox folder, and they'll be there for you. I think I have the PowerPoint right now, but I have some other stuff that I'll put in. And of course, I put the QR codes in using the pattern 1, 2, 3, with that. Anyway, I hope that there's something here that you've got from this. These sequences really are fascinating. They are so cool. And I hope that your students will enjoy them and that you will too. Thanks very much.
Thanks so much, Ron. We're going to start wrapping things up. As promised, one lucky winner is going to receive a TI graphing calculator of their choice. And tonight's lucky winner is Steve Breckner. So Steve, congratulations. We'll be reaching out to you over email to get a little more information in the next couple of days from you.
That's pretty cool. Mike, that's really
Start thinking about which calculator you want to grab. To download a certificate of attendance, go ahead and click the link in the chat window. Also listed the link for the documents that Ron said he'll be updating later as well. And if you're watching this on demand, go ahead and copy this link into your favorite browser to receive your certificate. So again, a huge thanks to Ron for persevering through everything over the past couple of days here. Thanks so much for putting this together. Lots of really awesome ideas that I think really span, elementary on up, which is a pretty unique thing to do. So thanks so much for everything you brought to us.
Absolutely. And Mike, do you want me to pop in the um, um, something? I can't do it immediately. I was going to put in the Dropbox link, but it's, what I'll do is I'll just put it back up in the screen, Mike. Can you see it right now?
Nope. Give me 1 second. I'll give you control.
Okay. Just as people are saying goodnight here, I'll just put this back up on the screen so that folks have this. So
and I
it's
can also include that tiny URL. I can include that in the follow-up email.
Good.
With the documents link, so we can make sure that everyone has a chance to get that.
Fantastic. Yeah, thanks to all of you for coming tonight. Kudos to all of you. You've taught all day long, and here you are at night doing some PD, and that's amazing. That's even more amazing than these sequences. So kudos to all of you. And thanks, Mike.
Thanks, everyone.